Ever wonder what it takes for a guitar to deliver a show-stopping performance night after night? Beneath the warm, soulful tone of a Gibson guitar is a battle of physics. Nearly 200 pounds of string tension held in perfect balance by an intricate internal frame. It's a design so precise that every vibration turns into pure acoustic power rather than lost energy. How did a century-old crafting technique master the laws of physics to create timeless sound? Subscribe to Discovery now to go behind the scenes and discover how iconic tools of expression are built to last forever. The electric guitar as we know it didn't come from a big lab. It came from a radio repairman. In the late 1940s, Leo Fender, who ran a small electronics shop in Fullerton, California, wasn't even a guitarist. He just understood amplifiers and magnets better than most working musicians did. In 1950, his company released one of the first mass-produced solid-body electric guitars, a plain, no-frills slab nicknamed the Broadcaster, soon renamed the Telecaster. Around the same era, Gibson answered with its own solid-body model, the Les Paul, in 1952. Both designs are still in production today, essentially unchanged in shape. Here's the number that still surprises people. One major American factory alone turns out somewhere between 350 and 900 guitars a day, depending on demand. And every single one still starts as a rough, unglamorous block of wood on a forklift. The process starts in a lumber yard, not a workshop. Workers sort through stacks of alder, ash, basswood, or mahogany, species prized for how they resonate, not just how they look. Each board gets visually inspected for knots, cracks, or weak grain that could snap under string tension. Boards that pass get loaded into a kiln, where they're slow-cooked at controlled temperatures for anywhere from several days to more than a week. Why not just use wood straight off the truck? Because fresh-cut lumber is full of trapped moisture. If you shape a guitar body from wet wood, it will warp, crack, or twist months later as it continues drying on its own, sometimes right in a customer's living room. The kiln forces that moisture out now, under control, so the wood is dimensionally stable before a single cut is made. Engineers on the floor say this step is invisible in the final product, but responsible for more warranty returns than almost anything else if it's skipped. Once the wood is stable, a rough-cut blank gets clamped onto a CNC router, a computer-guided cutting machine that can carve a guitar body in a matter of minutes. The bit spins at thousands of RPM, screaming through the wood as it hollows out cavities for pickups, wiring channels, and the control switches, following a digital template accurate to a fraction of a millimeter. But here's the part that seems backwards. Even with machines this precise, factories still route deliberately oversized on certain cuts, leaving material for a human sander to remove by hand later. Because wood isn't uniform, one plank might be slightly denser than the next, and hand finishing lets a worker feel for imperfections a laser can't always catch. The body is weighed at this stage too. Factories often sort blanks by weight, since a lighter body can change how a guitar resonates and balances on a strap. The neck is arguably the hardest part to get right, because it has to survive roughly 150 to 180 pounds of constant string tension without bending. A separate CNC pass carves the neck's profile and the truss rod channel, a thin steel rod embedded inside that lets a technician adjust the neck's curve later with a simple Allen wrench. Next comes fretting. Thin strips of nickel-silver wire are pressed into precisely spaced slots along the fingerboard, each slot cut to match centuries-old mathematical ratios that determine pitch. Why does fret spacing need to be accurate to fractions of a millimeter? Because even a tiny error compounds up the neck. A guitar that's in tune at the first fret, but drifts sharp or flat by the 12th fret, is unplayable, no matter how good it looks. After fretting, workers dress the frets, filing and polishing each one so a player's hand can glide without catching an edge. A single Stratocaster-style neck typically has 21 to 22 frets, and factory workers can dress an entire neck in just a few minutes once they're experienced. Now the body gets its skin. Workers hand sand the wood through progressively finer grits to erase any tool marks. Then it heads into a spray booth, where nitrocellulose lacquer, or polyurethane finish, is applied in multiple thin coats, sometimes 6 or more layers, with drying time between each. Because a thick coat traps solvents underneath, which can cause the finish to crack or sink months later as it continues off-gassing. Thin coats, built up slowly, cure evenly and bond tightly to the wood grain. Once the final coat is fully dry, which can take days, the guitar moves to buffing, a 3-stage process using a spinning wheel and polishing compound. The first pass knocks down rough spots. 2 more passes bring up a mirror gloss. Workers say you can tell an amateur buffing job instantly. It looks shiny under bright light but streaky in daylight, which means the compound wasn't fully worked out. This is where a guitar stops being furniture and starts being an instrument. A pickup is essentially a magnet wrapped in a coil of hair-thin copper wire. And that coil isn't wound a few dozen times, it's wound somewhere between 5,000 and 9,000 times around a bobbin, using a machine that spins at high speed while carefully guiding the wire so it lays flat and even. Why does it need thousands of turns instead of just a stronger magnet? Because a single strand of wire moving through a magnetic field generates a voltage too tiny to use. Stacking thousands of turns adds that tiny voltage together, turn after turn, until it's strong enough to drive an amplifier. Too few turns and the guitar sounds weak and thin. Too many and it can sound muddy and lose clarity. Once wound, the coil is potted, dipped in melted wax, to stop the wire from vibrating against itself and causing an unwanted howling feedback called microphonics. From there, workers hand solder the pickup to the volume knob, tone knob, and output jack. Dozens of tiny connections that all have to be right, because a single cold solder joint means dead silence on stage. Everything converges here. The neck is bolted or glued to the body, hardware goes on. Bridge, tuning pegs, strap buttons, and the pickups drop into their routed cavities. Strings go on next, but stringing up a brand new guitar is only step 1 of setup, not the finish line. A technician adjusts the truss rod to correct any curve in the neck, sets the bridge height so strings sit at a precise distance from the frets, and tunes the intonation, fine adjusting each string's length so it plays in tune not just open, but all the way up the neck. Why does a factory-fresh guitar still need a human to fine-tune it by hand, string by string, after everything was built to exact digital tolerances? Because wood keeps moving. Even after kiln drying and weeks of finishing, humidity and temperature can shift a neck by a hair's width, enough to throw off intonation that a machine can't feel but a trained ear and a tuner can catch instantly. Only after this final human pass does the guitar get plugged into an amp for a last sound check, played and listened to before it's ever boxed up. Crafting a guitar is an art of subtlety. But a banjo? That's a dangerous game of high-tension mechanics. On stage, a few light plucks can instantly trigger a massive,